All right, now we want to look at what happens when we have an incline. So in the figure at the right, we have an inclined plane, and again, we're going to assume frictionless for now. We will add friction in later videos. And we have a block sitting on an frictionless inclined plane, and the angle with respect to horizontal is given as theta. All right, so on the left, I have drawn a free body diagram for this situation. Now, again, we can choose a coordinate system any way we want to help us solve a problem. So since our motion is only going to be parallel to the plane, we want to choose a coordinate system so the motion is only in one direction. So I choose an XY coordinate system where X is parallel to the plane and Y is perpendicular to the plane. Thus, the motion is only in the X direction. But we have to resolve the weight now into horizontal vertical components. The weight vector, of course, mg, points straight down in the true vertical direction, which is going to be at an angle to the y-axis. So looking at the figure at the left, we can see I put in the angle theta for the incline of the plane with respect to the x-axis. That means that the weight mg forms an angle phi with the x-axis, which would be the complement of the angle theta. Thus, the weight mg forms the angle theta with the negative y-axis. So now, with mg as the hypotenuse, we have a little right triangle with the y component is one leg and the x component is the other leg. The x component is opposite theta, so that's going to be mg sine theta. The y component is adjacent to theta, so that's going to be mg cosine theta. All right, so we will have a component of the weight vector down the hill equal to mg sine theta and a component perpendicular to the hill of mg cosine theta. All right, let's look at an inclined plane example. So here I have an inclined plane inclined at the angle theta, and we're going to assume it's frictionless. We have a block sitting on the plane, and it's tied to a wall with a rope that is parallel to the plane. We want to find the tension in the rope, and part B, if the rope is cut, what will be the acceleration of the block? All right, so remember the previous slide that we had. We're choosing a coordinate system where the x-axis is parallel to the plane, the y-axis is perpendicular to the plane, because the motion then will only be in the x direction. So let's look at a free body diagram of this situation. All right, so here in the bottom I have a free body diagram. We've chosen a coordinate system where the x-axis is parallel to the plane and the y-axis perpendicular to the plane. The tension in the rope acts in the positive x direction. We have the normal force of the plane pushing up on the block, that's F sub n, that's in the y direction, and we have the weight of the block down, which of course is mg. All right, so the angle theta then will also be the angle between the weight vector downward with the y-axis. Thus, the component of the weight mg in the direction of the x-axis will be mg sine theta pointing down the hill. We will also have a component in the y direction of mg cosine theta. But since if there's any motion, it'll be only in the x direction. We don't need to worry about the mg cosine theta component for now. All right, so with the tension in the cord holding the block, we have static equilibrium. So that means the sum of the forces in the x direction must be 0. Well, we've got the tension force up the hill minus the component of the weight down the hill, which is mg sine theta, equals 0. So the tension just equals the weight mg times the sine of theta. So here's the solution. So the tension then is mg sine theta. All right, now part B. It says if the rope is cut, what will be the acceleration? Well, if the rope is cut, we no longer have any tension. The only force we have is the component of the weight down the hill, which is mg sine theta. So we set that equal to ma. So the acceleration is g sine theta. Okay, so this actually turns out to be pretty simple then. So the key is we want to write our coordinate system so the x-axis is parallel to the ramp and the y-axis perpendicular to the ramp. That way we only have motion in the x direction. All right, now we're going to look at a similar problem, but we're going to make it a little bit more complicated. Now we're going to put a pulley at the top and hang a weight off the back of the ramp. So we have an inclined plane with two masses tied together. We want to find the acceleration of the system and the tension in the cord. All right, now notice that this is exactly the same as the Atwood machine, but we've just added the ramp. Rather than having M1 hang straight down, we have it sitting on a frictionless ramp. So we're going to treat this one just like it was an Atwood machine. The only difference is that the weight component of M1 now is the component that lies along the plane, which we found to be mg sine theta in the previous problem. All right, here I've added a three-body diagram from the previous inclined plane problem. But notice that this would be the same free body diagram for the block sitting on the incline labeled M1. So we have a component of the weight down the hill would be M1g sine theta. All right, so we're going to do just like we did for the Atwood machine. We'll treat the two masses as a system. Then the only external forces that cause motion are the components of the weights in the direction of motion. So we'll do that now. All right, now before I write the equations for Newton's second law, I need to choose a direction for positive. Now it doesn't matter which direction I choose. Suppose I choose M1 up the hill as positive. That means M2 going down would also be in the positive direction. But I could just as well choose M1 going down the hill as the positive direction and M2 going up positive. And it doesn't matter. As long as I am consistent when I write my equations that I have the same direction as positive for both masses. If my acceleration turns out to be in the opposite direction that I chose as positive, I will just get a negative number for the acceleration. The magnitude of the acceleration will still be correct. So I'm just going to choose up the ramp as positive, and then we'll go ahead and write the equations that we get from Newton's second law. All right, so here I've put in the diagram a blue arrow indicating that up the hill for M1 is positive. That also means that M2 going down will be in the positive direction. All right, so now we're going to apply Newton's second law. The sum of the forces equals the mass times the acceleration. So we have M2g minus M1g sine theta. Remember, M1g sine theta is pointing in the negative direction, so that's why I subtracted it. And that's the sum of the forces, and that equals the total mass, M1 plus M2, times the acceleration A, or the acceleration equals M2 minus M1 sine theta quantity times G divided by the quantity M1 plus M2. So now if we're given numbers for the masses and a number for the angle of the plane, we would get a number for our acceleration. Now again, notice that if M1 sine theta was greater than M2, our acceleration would be negative, and the block would move down the hill and M2 would go up. All right, so here I've drawn a free body diagram for the block that's hanging off the back. It has the mass M2. So I have M2, and the forces acting on M2 are its weight downward, M2g, and the tension pulling up on it. But remember, we chose for our positive direction as M1 going up the hill, which meant M2 going down is the positive direction. So in this case, the weight M2g is in the positive direction, and the tension is in the negative direction. So now I apply Newton's second law. The sum of the forces equals ma. So I've got M2g in the positive direction minus the tension in the negative direction equals the mass M2 times its acceleration. This is the same acceleration we found in the previous step. So solve for t, and I get t equals m2g minus m2a. Factoring out the m2, we get the tension equals m2 times the quantity g minus a. Now again, if we had been given numbers for the masses, we would have a number for the acceleration. We just plug that in, and we would get a number for the tension. All right, one thing I want to point out here, because I've seen students make this mistake a lot. They'll look at the free body diagram for M2 and just assume the tension equals the weight of M2. Well, that would only be true if we were in equilibrium and there was no acceleration. But since we are not in equilibrium, then the tension will not be equal to the weight. So be very careful of that when you are working your own problems. All right, so we're finished with this one, but let's go ahead and do a free body diagram for M1 just so that you can see how that one would work out and give us the same tension. Okay, here I have the free body diagram for M1. We have the tension force pulling up the hill, and we've got the component of the weight down the hill, m1g sine theta. So we apply Newton's second law to m1. The sum of the forces equals ma. So we have the tension minus m1g sine theta as the sum of the forces. That equals m1 times the acceleration. Solving for tension, we get m1g sine theta plus m1a. And then factoring out m1, we get the tension equals m1 times the quantity g sine theta plus a. So again, if we were given numbers for the masses, we would have a number for the acceleration, and this would give us a number for the tension as well. All right, so we didn't have to do this step. We could have done either one to get the tension in the cord. All right, let's look at one more inclined plane problem that's slightly more complicated. So the situation here, we have a rope tied to a crate on a frictionless incline, and the rope is pulling the crate up along the hill at a constant speed. We're given that the crate has a weight of 200 newtons, and the hill is inclined to the horizontal at 15 degrees. So again, it's moving up the hill at a constant speed. Constant speed in a straight line means constant velocity. Constant velocity means there's no acceleration. So this is an equilibrium problem, but since there is motion, it's dynamic equilibrium. But in either case, equilibrium means that the sum of the forces must be zero. So next, we'll draw free body diagrams and put in all of the forces and then apply Newton's second law. All right, so in the bottom diagram now, I've put in all of the forces and their components. And notice that, like the other inclined plane problems, we're choosing a coordinate system where the y-axis is perpendicular to the plane and the x-axis is parallel to the plane. Thus, the motion is only in the x direction. So we have the weight vector, mg, pointing straight down. It has a y component of mg cosine 15 degrees and a component down the hill of mg sine 15 degrees. The plane also pushes up on the crate. That's the normal force, F sub n. That's only in the y direction. The tension in the rope, that vector is at 35 degrees with respect to the horizontal. But the tension then is only 20 degrees with respect to the x-axis. Since the x-axis is tilted at 15 degrees, we take 35 minus 15 to get 20 degrees for the tension force with respect to the x-axis. Thus, the x component of the tension force is T cosine 20 degrees. The y component of the tension force is T sine 20 degrees. Now, since we are in equilibrium, that means the tension force up the hill will equal to the weight down the hill, since the sum of the forces in the x direction must be zero, since we have no acceleration. So now we can write our equations. All right, so now that we have the vectors and their components, and we know that their is a constant speed or no acceleration, the sum of the forces must be 0. So in the x direction, we have t cosine 20 degrees up the hill minus mg sine 15 degrees down the hill must be equal to 0, or t cosine 20 equals mg sine 15, or t equals mg sine 15 divided by cosine 20. Now I substitute 200 newtons for the mg, then times sine of 15 degrees and divide by cosine of 20, and we get 55 newtons for the tension in the rope. Okay, so now we've solved the problem. We found the tension in the rope that pulls the crate up the hill at a constant speed. But I want to point out one thing here that you should be careful about, because I've seen students make this mistake many, many times. Some of the problems, they'll give you the weight in newtons, and sometimes they'll give you the mass in kilograms. So notice we were given the weight in newtons. So mg equals 200 newtons. The mistake I see is students will take the 200 newtons and multiply by g, assuming that this is the mass in kilograms. So no, if they give you the weight in newtons, mg is the weight. So we replace the mg with the weight of 200 newtons. We do not multiply by g again. No, if we were given the mass as 200 kilograms, then we would have to multiply by g to get the weight. But since we were given the weight, mg is the weight. So be careful about that. All right, so that's the end of this video. So in future videos, we will look at some more Newton's second law problems, but this time we'll look at what happens when we add in friction. And I'll also do a video on centripetal force as well. All right, so if you have any comments or questions, leave them in the sections below, and I'll try to answer all of your questions. Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.